Hi, this is your first video for Chapter 19. Chapter 19 is about energy and using energy methods to solve problems involving electricity. I want to review first a problem that we did last semester that has to do with energy and that has to do with gravitational potential energy. Afterwards, we'll do a very similar problem about electric potential energy. So pause for a moment and read the problem here. All right, so we've got a picture. There's a basketball. There's two different locations of it. We notice that the force of gravity exerts a downward force at it at all times. And we are asked, calculate the change in the gravitational potential energy of the ball as it moves from point A to point B. It's dropped from A to B. Now, one thing about notation, in the book, they write GPE for gravitational potential energy. I'm not going to use that. If I need to distinguish it, I'm just going to write a PE sub G here. All right, so a few things to remember. The equation for the gravitational potential energy is equal to the mass of the basketball times the gravitational constant G times the height h of the ball. Another energy term we'll use a lot here, kinetic energy, recall, is equal to 1/2 times the mass of the basketball times the speed squared of the basketball. Now, to calculate the change in potential energy at part A, we're going to need to figure out what it is at A and B and calculate the difference, right? Remember that when you are figuring out the potential energy, you're free to choose the zero reference point of your height. I'm going to go ahead and make the location HB equal to 0 for simplicity. And I know B is 2 meters below A, therefore up A here, the height of A is going to be 2 meters. Now, let's go ahead and calculate the change in the gravitational potential energy here. As usual, the delta symbol means PE final minus PE initial. The final position is at position B, right? So this is going to be our B here. We start at A. This is our A. And so we're going to have MGHB minus MGHA. Now we do have a 0 value here for HB. So this whole term is going to be 0. And if we see what's remaining, we just have an MGHA. And we can plug in the numbers here. 2 kilogram mass, 9.8 meters per second squared, and HA is equal to 2 meters. Put that into the calculator, and we get a value of 39.2, and the units are going to give us kilograms, meters squared per second squared. This guy, that's a joule right there. So we end up with 39.2 joules. Oh, I forgot something. What did I forget? There's a minus sign there, right? Negative 39.2 joules. So the potential energy is decreased because the ball has fallen down from a higher to a lower potential energy. Let's look at part B. The work done by the gravitational force. Well, the gravitational force pulled it down and it moved down, so its displacement has been in the direction of the force. It's sped up. That means the force has done positive work. And in fact, there's a real simple way, because gravity is what we call a conservative force. Whenever that's the case, we can directly relate the work done by the force with the change in potential energy for that force. And just to remind you real quick, that is, the work is simply equal to the negative change in the potential energy. So the work here done on the basketball by gravity is going to be minus delta PE, and in this case, a minus 39.2 joules. Let's look at part C. Part C says, calculate the change in the ball's kinetic energy. All right, let's go back to that sheet we looked at a second ago. Gravity is a conservative force, which means that we have this conservation of mechanical energy. It says that the total mechanical energy, which is the sum of the potential plus the kinetic, equals a constant value. Or in other words, the change in delta PE and delta KE must cancel out exactly. So let's go ahead and write that down, right? So what we're saying here is that E mechanical, the change in that mechanical energy, well, that's going to be the change in the potential energy plus the change in the kinetic energy. And that's going to be 0 for a conservative force, right? In other words, you know, if the PE goes up, the KE goes down by an equal and opposite amount, and vice versa, right? We can use that equation now to solve for the kinetic energy quite simply. So just doing a little bit of algebra, we can see that delta KE is going to be equal to minus delta PE, which is going to be minus, well, delta PE is a negative 39.2 joules. Minuses cancel, and we come up with 39.2 joules. For part D, we're asked to calculate the speed of the ball, and you'll probably remember doing this. In this case, if we know the kinetic energy, we can figure it out, right? So delta KE, right, that equals KE final, which is the lower point. If we look back at the map, KE final here is point B, minus KE initial, point A. Let's go ahead and put in our equations for KE. So delta KE, well, we know what that number is. And this is going to be 1/2 m, the speed at point B, minus 1/2 m, the speed at point A. Square those speeds. Now if we go back and go, remember, it starts from rest, so the speed here at point A equals 0. And so we can go ahead and plug that in here. That's a 0. And we've got this simple equation now. I'm going to just flip the directions of the speed here. So I'm going to have 1/2 m VB squared is equal to delta KE. Now we know all the data, we can solve for VB. So let's go ahead and do it. VB is going to be equal to, I need to, let's see, multiply by 2, divide by m on both sides. Right, we're going to get some cancellation here, and I'm going to have to do a square root of that term. So I'm going to end up with a 2 delta KE over m square root. Let's plug our numbers in and see what we get for this value. 2 times 39.2 joules divided by 2 kilograms. It's all positive in there, so we got positive under the root, exactly what we want. Put that in the calculator and we get a number equal to 6.26 meters per second. We always take the positive root because speeds are always positive or 0. So this is a review of what we've done before in Physics 2a. All of this same stuff, we can apply this again to Physics 2b in the case of the electric force, because the electric force is also a conservative force. So let's skip over to that problem real quick here. Take a moment to read this and look at the picture. It kind of looks like the picture before. Now instead of a ball, we've got a cloud, we've got the ground, and we've got charge separation, which can happen because of friction. So in part A, we're asked to calculate the change in a proton's electric potential energy as it moves from the cloud to the ground. In this problem, we are told that there's an electric potential of the positively charged cloud that has a higher value by 1.5 times 10 to the 8th joules per coulomb than the electric potential at the ground. Now let me be careful, because the words we use in this stuff is really poorly chosen. So electric potential energy is different than electric potential. And remember when we did gravity, right? We said PEG is equal to mgh. Well, I want to think about this GH as being, this would be called the potential if we were talking about it in terms of gravity. And notice that I multiply this GH by m, and then I get the potential energy of gravity. Now for the electric force, it's the same idea. I'm going to call it potential energy electric. We're going to, instead of mass, we multiply by the charge to be able to get the potential energy. So there's the charge, and now we need to put in this so-called potential. We call this the electric potential. And it simply has a variable V. And so electric potential, that is what V is. Now, if we have a change in V, delta V, we call that's of course V final minus V initial. The change, this is called the electric potential difference. Or another word to use is the voltage. They mean the same thing, electric potential difference or voltage. All right, so we're going to go ahead and do part A here. Just like we did with the gravity problem, there's a change in the electric potential. It has a different value at 2 points. Well, it's going to be changing along the vertical axis because up here it's got one value, down here at the ground it's got a lower value. So it's similar to the gravity problem in this particular case because of the way it's lined up. And so up at the top we're going to have one value because again the proton is going to move from the cloud to the ground. So this is your initial here. And down here is your final value of the electric potential. And I again can choose my zero wherever I like. So it's greater at the cloud than it is at the ground. It's always higher where positive charges are. I'm going to call the ground 0 in this case. And so up here, the potential is going to be equal to this number. That much greater than the ground, which we set to 0. Calculate the change in the proton's electric potential energy as it moves from the cloud to the ground. Well, let's go ahead and do that. So delta PE electric, I'll usually just ignore the E because we'll always be electric in this chapter. That's going to be PE electric final minus PE electric initial. We have an equation for that, right? So that means take the charge, multiply by the final electric potential, charge, using this equation, right, times the initial electric potential, right? There's really two ways you can do it. If you want, you can go ahead and just factor the charge out and directly multiply by the electric potential difference or the voltage. It doesn't matter either way. In this case, the final is equal to 0, right? I'm going to go put that to 0. So we got a simpler equation now. It's just going to be delta PE is equal to minus Q V0. We have all these numbers, so we got a negative. Q in this case is a proton, right? So that means positive 1.6 times 10 to the minus 19th coulombs. The electric potential at the initial position, it's this number here, 1.5 times 10 to the 8th joules per coulomb. Notice that you multiply that by a charge, the electric potential, and it turns into an electric potential energy. And so the change in electric potential energy here then comes out to be, when we plug this into the calculator, 2.4 times 10 to the minus 11th joules. Now it's a small number because protons are very tiny. And there's also other units we can use. Electron volts is another unit of energy that is a smaller unit. Sometimes we use that for tiny things like electrons and protons. So in any case, let's think about if this makes sense, right? If you had a proton up here, where is it going to want to go due to the electric force? Well, it wants to get away from the pluses, it wants to go towards the negatives, right? Because of that, it's moving closer to the negative where it wants to go. The potential energy is going down. It was high when it was close to the positives that are going to push it away hard, and far away from the negatives that will attract it. So as it gets closer to where it wants to be, its energy is decreasing. It spontaneously moves towards the negative. So it makes sense that we have a negative. I forgot to write it here, so let's make sure we put that in there. All right, part B. Part B is going to be easy. Calculate the work done by the electric force on the proton. Well, you know the electric field lines, they go down from positives They terminate on negatives. So we got electric field is going down. That means the electric force is going to be going down on the proton. And the proton moves with the force. The force is going to do positive work on it, just like we saw the gravitational force pointing down did with the basketball as it moved down. And so we can use the same equation as before. The work done by the conservative electric force on the proton is going to be equal to minus the change in the potential energy of the proton as it goes from the cloud to the ground. And we know minus minus, it's going to simply come out to 2.4 times 10 to the 11th joules. That is the work done by the electric force, essentially by the other charges, the charges in the cloud and the ground, causing the proton to be moved from the cloud to ground. And in a sense, this energy that's released, this work that's done, right? This is actually what happens when we have lightning, right? You see, you hear a loud noise, that's energy in the sound wave. You see a flash of light, you generate a lot of heat. These are all forms of energy. This is what that work is turning into.